Today we're going to look at the knowledge area electricity and magnetism. Electrostatics is a topic that falls within this knowledge area. Alright, now we know that the phenomena of electrification can manifest itself in a number of ways. I have cited a few events. We know that you get an annoying shock is experienced when a door handle is touched after sliding over a plastic seat. Right? Also, a shock is felt after walking on a woolen carpet and then touching a doorknob. Another situation is the slight crackling of sound is heard when dry hair is brushed, right? And then we also know that the tendency of sheets paper attracted to a rubber comb, right? We've seen this. You got a ruler, you rub it through your hair, and you can pick up paper. Now, this phenomenon that you observe at a macroscopic level, we see this at an observable level, and we trying to explain what actually happens at a micro level, right, or at a microscopic level. Now, electrification is a process of establishing an electrical charge on an object, right? Whether that charge is a positive charge or whether it's a negative charge, we are trying to establish the charge on an object, right? The object is said to be charged with electricity, right? Whether it is a positive charge or a negative charge, we say that it is charged with electricity. And electrification is most apparent when air is cool and dry. Normally on a humid day, when you do the experiments, they don't work too well because the charges on objects actually leak out into the atmosphere. And electric charge is confined to the object, right, is said to be an electrostatic charge. Static meaning stationary. Then static electricity is produced by friction between two surfaces in close contact. So when you have two surfaces rubbing each other, we find that an electric charge can be established. And then static electricity, we say stationary and in the form of a charge in equilibrium. Okay, so static electricity is produced by friction between two surfaces in close contact. Right. Now that we have an idea of the notion of electrification, we would like to explain what happens at a microscopic level. And I'm going to illustrate that by using our model of an atom, right? So here, for instance, I have a carbon atom. So I have a carbon atom, and we know that the atomic number of carbon is 12, and the mass number, the atomic number is 6, and the mass number is 12. What does this indicate to us? We know that here we've got 6 electrons, okay, and we know that we got 6 protons. Alright. And since the two particles are, in terms of their charges, you got 6 negatives and 6 positives, we say that the carbon atom is neutral. It's neutral. Now here are represented a carbon atom, but remember, if we're dealing with a carbon rod, we have a whole lot of these carbon atoms, thousands and thousands of carbon atoms. I have but represented one here just to illustrate what happens when this particular rod is rubbed with a material. For that matter, let's say if it is rubbed with a cloth, and this could be silk. Okay, can be silk or it could be fur. So and we know silk has its own atoms as well, and we have positive and negative charges, right? And if the silk is neutral, that means we have equal number of positive and negative charges. Now what happens when a silk rubs a carbon rod, or for that matter any other material? We try and explain what's happening at the microscopic level. Now we know that our protons are all in the nucleus of the atom. The electrons are the particles that move around the nucleus. So these electrons are held by the force between the nucleus and the electrons, right? And here I'm considering the electrons in the outermost energy level because they can be lost easily. So if the force between the nucleus and the outermost energy level is not too strong, those electrons can be lost. So what happens is, if silk is rubbed with silk and a carbon rod are rubbed, we find that if, for instance, the carbon loses an electron, and if it loses an electron and the silk gains an electron, then in that particular case you will find that carbon will then have a positive charge, which I indicate like that, because now it's going to have more protons than electrons, and the silk would then have a negative charge, implying that it has more negatives than positive. If for instance the silk loses an electron, we find that the silk would then be, say in that case, if it loses electrons, the silk would be positively charged and the carbon would be negatively charged. So at the microscopic level, at the subatomic level, we have an indication of what happens when materials are rubbed together, right? Now, all materials we know contains positive and negative charges. And a neutral object has an equal number of protons and electrons. But if the charge on the object is positively charged, the object is electron deficient. object or a particle that has a positive charge means it has less electrons as compared to protons. A negatively charged object always has an excess of electrons. So a negatively charged object has more electrons than protons. A positively charged object has less electrons and more protons. And what's also important is that only electrons are transferred when materials are rubbed together. That means electrons are either lost or electrons are gained. The protons are in the nucleus, they do not get transferred. Now, here we have a triboelectric series. This triboelectric series essentially gives us an indication of the ease with which material loses or gains electrons. Right? And this gives us an indication of the relative ranking of these materials. So, here you have, for instance, at the top from wool, rabbit fur, hair, glass, mica, and wool, they tend to lose electrons. They tend to lose electrons. Whereas, like the bottom ones, silk and all that, tend to gain electrons. But if we look at the ranking here, say for instance, if I take rabbit fur and I rub it, let's say with rubber, right? What would happen is the rubber would gain electrons, it would gain electrons and it would be negatively charged. And the fur would lose electrons and it would be positively charged. Let's look at another one as well, because I'm going to be dealing with this a bit later when we deal with the electroscope. Here I have a glass rod and I have silk. And if a glass rod is rubbed with silk, silk becomes negatively charged and a glass rod becomes positively charged. So a glass rod rubbed with silk, the glass rod becomes positively charged and the silk becomes negatively charged. Right. So these charges, the charges on these material have been established, and the charges are arbitrary in the sense that by convention we assign a positive charge to certain material and a negative charge to other material. So if we look at this now, here we have an electroscope. So in the presence of an electroscope, charge can be observed, right? An electrostatic charge can be observed by using an electroscope. Now there's different types of electroscope. We're going to deal with the simplest kind, and then I will draw your attention to a more sensitive electroscope. So electroscope, the simplest kind, is essentially a small push ball suspended on a silk thread, and the ball is coated with aluminium or graphite, right? Graphite and aluminium, the conductors. And then a more sensitive electroscope has gold leaf and an aluminium leaf electroscope. But I will just briefly show you the components of these, since it has its applicability on whether material is a conductor or an insulator, but that I will do later in a section. Now let's say, for instance, suppose we have a rod and it is charged with flannel, right? We saw that if we have a rubber rod and it's rubber flannel, the rubber rod becomes negatively charged. Now, if the rod is held near a simple electroscope, we find that the pith ball gets attracted. Right, so here we've got a rod, we bring it close to this pith ball which is neutral, and we find that the pith ball gets attracted. If the pith ball is then allowed to make contact with the rod, it immediately rebounds and is then repelled by the rod. So here you have this phenomena. When it's brought near the pith ball, it attracts, and when it touches the pith ball, it repels. Now let's have a look at it in this illustration here. Here you got your pith ball is neutral. There you got your charge rod. What happens, we know, and we've dealt with that these charge rods, and where an object is charged, it has an electric field, right? And so positive charges have a field, negative charges have a field, and we have alluded to how these fields are formed. But here now we have this negative charge rod, and we find that the pith ball is neutral, so it has an equal number of positive and negative charge. Under the influence of the fields, you find that your electrons in the pith ball move towards the end here, and then what happens is the positive charges are near the rod and the pith ball gets attracted. So it gets attracted. But here you find that once contact is made, what happens is once contact is made and the rod has excess electrons, the charges flow into the pith ball. And as the charge flows into the pith ball, the rod and the pith ball have the same charge, and then we find that the pith ball repels. So when the rod is brought near that pith ball, the particular pith ball repels. And it would be reasonable to assume that charge has been transferred, right, from the rod to the pith ball, right, and they are now similarly charged. So if I now bring a positive rod near this negatively charged pith ball, if I bring a positive glass rod, you find that it exhibits a different phenomenon. That means with the negative rod, the pith ball was repelled, and when we bring a positively charged rod, we find that the pith ball gets attracted. And this manifestation essentially indicates that you have two different types of charges on the rod. Right. So here are essentially just verifying that we have two different type of charges. And from here we can then conclude that the charges produced in the rubber and the glass rod are opposite in nature. Now there are two kinds of charges, and we say the one where we have a rubber rod and rubber flannel, it has a negative charge, and a glass rod, rubber silk, has a positive charge. Okay, so we have two different type of charges. And surely we is these type of experiments that eventually also contributed towards our understanding of the atom and the fact that it has different type of charges. Here we have a leaf electroscope, and as I mentioned, I will just give you an indication of its components, because if we want to understand a bit more about conductors and insulators, we need to know how an electroscope actually works. So the electroscope is more sensitive than the simple pulse ball. It consists of gold leaf or aluminium foils. It has a metal knob, right? And the leaves are enclosed for protection, and the metal stem is insulated from the case. And when electrified, the leaves diverge because of repulsion between similar charge. Now let's just see here. I've said that, but let's look here. We have here metal pen, right? Here's the foils. This whole thing here, from there is your metal, right? And there you have your glass, which insulates the conductor, so no charges can leak, right? So if we look at this here now, and we know, for instance, this particular metal conductor will have positive and negative charges, and if it's neutral, it will have the exact amount of positive and negative charges. Right, now if you bring a negatively charged rod here, you find what happens also, because remember it has an electric field, and what happens is the electrons are pushed to the leaves here, and the positive charges remain, and then we find that these leaves repel each other, right? So when you have like charges, they repel each other. Same thing happens with a positive. What happens in this case is you have the negative charges moving towards your metal pen, and the positives remain on the gold leaf, right? And we find that, or that foil, and we find that there's repulsion as well. So this just illustrates what happens when a negative and positive charge is brought near the metal pen of an electroscope. And we will use this when we want to illustrate the idea of insulators and conductors later. Right, now forces on charged objects which are brought close together. So if we have two pulse balls that are negatively charged by contact, like for instance we had a pulse ball that was negatively charged by the rubber rod, right? We find they repel each other. If we have two pulse balls that are positively charged, we also find that they repel each other. However, a negative charge pulse ball brought near a positive charge pulse ball attract each other. So here we have an indication of the illustration. If we have two positive charges, we find that they repel each other. If we have a positive and a negative, we find that they attract each other. Right? They attract each other. The forces are inwards. Here we show again two positive charges. There's repulsion. So these similar charges. When it's similar charges, they repel each other. And if they are positive and negative, here they attract each other. Right, and this is it also gives us an indication how the electrostatic fields interact. Right, but that's not part of our study in this particular lesson. So the observations can be summarized by a basic electrostatic, which means that similar charges repel each other and unlike charges attract each other. So if we look at this now, if for instance we have a force of repulsion. So what happens to this particular force of repulsion? As you will see, I've drawn it. It's drawn in a way they are equal in magnitude, these forces, but they are opposite in direction. Right. So what would happen if the charge on this particular object, let's say instead of it being +1, it is then +2, right? Or let's say there are two positive charges instead of +1 positive charge. So we say, right. So what would happen to the force? We know that the force between these two particles would be greater if the distance between the charges are the same. Alternatively, if the distance between the charges are the same, if the distance between the charges are the same and the charges increase, the force between them would increase. But if the charges are the same and the distance increase, the force between these charged particles would decrease. So I'm just giving you a qualitative picture of that because in grade 11 you will quantify the force. So here I've just shown you that the size of the force, right, either attracts or repel, and the size of the charges of the objects, the greater the charge, the greater the force of attraction or repulsion. And the distance, if the distance between the objects, the smaller the distance between the charged objects, the greater the force, right? And like I said here, the exact relationship is known as Coulomb's law, which you will do in grade 11. Right, now let's look at charge. Firstly, we know an atom is made of positive charges and negative charges. And the charge on a proton, I have shown it here, and it's approximated to 1.6 times 10 to the minus 19. It's plus 1.6 times 10 to the minus 19. The electron has the same charge, but I have just given the charge here in terms of, I've written it out, it's got 9 decimal places, right? So why I have done that is basically because the SI base units are now linked to natural constants, right? So the base unit ampere is linked to the charge of an electron. The charge of an electron is one of the 7 natural constants that we have. And the SI base units are now linked to natural constants, and over time they have been delinked from physical prototypes. Like in the past, we used to link our mass to the mass of a kilogram mass kept somewhere in Paris. So now base units are redefined in terms of natural constants from the 20th of May 2019, all our base units, right? Which means kilogram, mass, ampere, temperature, they have been redefined in terms of these natural constants. Like for instance, our mass of an object is now defined in terms of Planck's constant. And this hasn't yet been made explicit in our textbooks, but as time elapses, they'll probably do that. And the other thing is that the charge on an electron is fixed. The charge is fixed. This particular number is an exact number, right? And by definition, it is equal to what I've given you, and it is minus 1.6021766634. It's fixed, but we are not going to be using that. I just wanted to illustrate the point that the ampere or the unit of current is defined in terms of the electron. Right, we're going to use it as 1.6 times 10 to the minus 19 coulombs. Right, so the proton has an equal charge but opposite in sign. So 1 coulomb has a charge. So 1 electron has a charge of 1.6 times 10 to the minus 19. And how many electrons make a coulomb? 6.25 times 10 to the 18 electrons make 1 coulomb. Right, and as I've alluded to earlier, in a neutral atom, in a neutral, so in a neutral, that has to be out here. In a neutral, not real atom, in a neutral atom there are the same number of protons and electrons. Now let's look at the distribution of charge. Friction or rubbing can cause a charge to accumulate on an object. Charge can be distributed by 2 processes. One is contact and the other one is induction. So the one the rod touches a particular object, and the other one where the rod is just brought near a particular object. Now let's look at charging by contact. If we have a charge on an insulated stand and it touches an uncharged or a charged sphere, here I'm showing that it touches a charged sphere, the object will then share their charge according to their size. Identical objects will have equal charges, and in our situations we deal mostly with identical objects. Right. So let's look at the charge on our two spheres. One has a charge of 4 times 10 to the minus 6 coulombs, or we could have just said minus 4 microcoulombs, and minus 8.0 times 10 to the minus 6 coulombs. So these charged spheres, they then make contact. So they make contact. Once they make contact and then they separate it, right? So they make contact, they make contact, and then they separate it, right? So they make contact there. So we want to know how are these charges distributed. So firstly, you can see this charge is minus 8.0 times 10 to the minus 6. This one here you can see is minus 4. So what happens here is your one sphere is more negatively charged than the other sphere. And being more negatively charged than the other sphere, we find that electrons move from the more negative to the less negative sphere. And at the end, we said that they have equal charges. So what is the charge on each sphere after separation? If we want to determine the charge on each sphere after separation, so we know the one is minus 4.0 times 10 to the minus 6 coulombs plus maybe let me just do it here. So one is minus 4.0 times 10 to the minus 6 coulombs plus minus 8, right, 0.0 times 10 to the minus 6 coulombs, right? And that divided by 2 is equal to minus 12 times 10 to the minus 6 coulombs divided by 2, and that is equal to 6 times 10 to the minus 6 coulombs. Minus 6 coulombs. Okay, so minus 6 coulombs. So each one, and sorry, that's a charge of minus 6 times 10 to the minus 6 coulombs. Right. So we see that each one has a charge. What has happened here now, you had minus 8, the one was minus 8 times 10 to the minus 6, and the other one is minus 4 times 10 to the minus 6, and then at the end you have this one having a charge of minus 6 times minus 6 minus minus 6 times 10 to the minus 6 minus 6 coulombs, and this one here will have the same charge, 6 times 10 to the minus 6 coulombs. Both have the same charge. And having the same charge there, obviously, I mean, if they could, if they were suspended, they would then repel each other, right? Okay, now we go to charging by induction. In this situation, the object to be charged does not touch the other object. The following diagrams shows the distribution of the charge. So when the charge rod is brought near an insulator, and the next one when the charge rod is brought near a conductor. So here you have an insulator. Right, here A, B, you've got a charge rod. Okay, and C gives you an indication of the molecule. What happens is when you have a positively charged rod brought near the vicinity of this insulator, you find that the molecules or atom for that matter in the vicinity of this charged rod, they're going to be affected by the electric field of this rod, and we find that the charges within the molecules are moved in a sense that the electrons within the molecule are slightly moved away from the protons like that. So let's say, for instance, we have a neutral substance and it has molecules. So the molecule is made of protons and electrons. So the molecules are neutral. But what happens in the vicinity of a charged object, we find that the positive rod here is going to attract electrons, and then there's a slight shift in the centers of positive and negative charges within the particular atom or molecule. So we then say that the molecules become polarized. Right. Remember, the molecule is neutral. They're neutral. The only thing is now the centers of positive and negative charges do not coincide, so the molecule has a slightly negative side and a slightly positive side, right? And the molecule gets polarized. And if we now charge a conductor, but here I've said insulated conductor, reason being then the charge doesn't leak away from the conductor. And if we have a positive rod here again, and if we have here a conductor, like we could have a metal, okay, and we know in terms of metallic bonding that electrons are delocalized. Electrons are delocalized within metals. So what happens, it means those electrons can move freely around the metal. And if we have a positive rod here, what happens that your electrons, because they can get delocalized, they come close here, and we find that there's attraction. Right. So in this sort of situation, remember what happens when we're dealing with a conductor. The electrons move through the system, and whereas in an insulator, the molecules are actually polarized, right? It means the one end of a molecule becomes slightly positive and the other end negative. Whereas in a conductor, the electrons are actually separating from the protons, and there's a separation of charge. The one region becomes positive and the other region becomes negative. So when we're dealing with insulators, they become polarized, and the rod, when the charge rod is brought in its vicinity, right? And what happens there is because the center of positive and negative charges do not coincide. So the rod has an influence on those molecules, and it changes its behavior. And then in the case of the conductor, is also polarized, but there is a movement of electrons and a separation of charge. Right, so both are polarized, but an insulator is polarized differently. The atoms actually, or the molecules, have regions of high and low charges. For instance, one area may be positive and the other one negative. Now let's look at the transfer of electrons. Electrons get transferred from a more negatively charged object to a less negatively charged object. Right? So where there's more electrons and there's less, it always moves from more to less. Then negatively charged to a neutral object. Then from a neutral object it moves to a positively charged object. And then from a less positive charge to a more positive charge. Okay. So what we're saying, let's say for instance we have here we've got AB, and let's say A has a charge of say let's say minus 2 coulombs. Right? And the minus telling you that it's got extra electrons. And let's say it goes to, and that has a charge of minus 1 coulomb. So what happens in this case, right? So from a more negative to a less negative, we find that electrons move that way. Right? From the more negative to the less negative. If we have a negatively charged object, and let's say it's a minus, say 1 coulomb, and let's say that's neutral, and we also find electrons moving in that direction, like that. And then let's say we have a neutral, and this is positively charged. We also find electrons moving from the neutral to the positive. So the positive is deficient in electrons. And then let's say we're moving from a less positive to a more positive, say 2 coulombs. Also find electrons moving from there to there. Alright, that gives you an illustration of the direction in which electrons are transferred. So sometimes we can sort of look at this in a different way. Say, for instance, if I say, okay, I've got 0, I've got plus 1 coulomb, I've got plus 2 coulombs, and I've got plus 3 coulombs, I've got minus 1 coulomb, minus 2 coulombs, minus 3 coulombs, like that. So what I'm saying is, essentially, if we say move from minus 2, so let's say maybe this area here, that's neutral, right? This side is positive, and this side it's negative. So if it moves from a sphere having a minus 2 there, we find that electrons are transferred. And from minus 1 to 0, we find electrons are transferred. And from 0 to, say, plus 1, we find electrons get transferred. And so as well was here to there. As it moves towards the right, electrons get transferred. As you move towards in the left direction, say from plus 3 to plus 2, we find that electrons are lost. Okay, so that gives you an idea. Now let's look at the conservation of charge. Conservation of charge, if we look at this here, the net charge on an isolated system remains constant. Right, the net charge on an isolated system remains constant. And like we said, only electrons can be added or removed from a system. Right, but what does an isolated system mean? What does an isolated system mean? Right, an isolated system is essentially a system. So let's say if I have an isolated system here, let's call this our system. And let's say in this system I've got my 2 particles, right, with their respective charges. Now an isolated system is a system in which no matter or energy can move to and fro. So let's say this is the boundary of that particular system. We choose it to be our boundary because we want to investigate what's happening in the system. So for instance, if we have matter and we have energy, matter cannot move in and out of the system. So matter cannot leave the system, matter cannot enter the system. Energy cannot go out of the system, energy cannot come into the system. So then that system is isolated. And in physics, we're going to be dealing with isolated systems. In chemistry, we normally deal with open systems and closed systems. Right, that is defined differently. So if we look at here now, our charge in that particular system is given by this equation. Q nu, that means if we have 2 spheres with the charges, say Q1 and Q2, and they touch each other and then separated, then what is the new charge on each of those spheres? Here we have giving you an indication. For instance, if I have charge A, sphere A with a charge of 12 plus and sphere B 0, that means the total positive charges is plus 12 before they interact. Before they interact, right? So it's plus 12. Then they touch. After they touch, they separated, and if we add them, it's also plus 6 and a plus 6. So a plus 6, and that gives us, maybe let's just say plus 6. And plus 6, which gives us plus 12. That means our charge is conserved, right? And if we're dealing with an isolated system, the charges we start with is the charge we end up with, total charge. Right, now let's look at example 2. Let's look at example 2. So here now, if we have the one object having a charge of minus 3.6 nanocoulombs and the other one has a charge of 4.8 nanocoulombs, and then they touch each other, right? Charge of 3.6 and the other one, and then they touch each other, and we want to calculate the charge on each object after they touch. So we say, okay, Q nu is equal to Q1 plus Q2 all upon 2. Right? We then say that is equal to minus 3.6 nanocoulombs plus a plus 4.8 nanocoulombs divided that by 2, which gives us 1.2 nanocoulombs, and that gives us plus 0.6 nanocoulombs. Right, so that means each sphere after touching would have a charge of 0.6 nanocoulombs. So that means each sphere there and there, the one was minus 3.6 and the other one was plus 4.8. So what happens in this case is that electrons move from there to there, and we find that afterwards each one has 0.6 nanocoulombs, and that one has also 0.6 nanocoulombs. So how much charge has been transferred? If you look at this, that's 0.6. So the total charge that's transferred would be 4.2 nanocoulombs, right? So if we have a charge of plus 4.8, and when 4.2 nanocoulombs is transferred, the resultant charge on that sphere would then be 0.6 nanocoulombs. Likewise for the other one as well. Right, now let's look at the exercise. If we look at the exercise here and we say an object with a mass of 3.6 nanocoulombs touches an identical object and during contact 1.8 nanocoulombs of the negative charge object is transferred to the neutral. An object with a charge of minus 3.6 nano touches an identical neutral object. During contact, 1.9 of the negative charge object is transferred to the neutral object, and then they both are separated. What is the charge on each? Okay, right? So if we look at that, we say, okay, we have one which is minus 3.6 nanocoulombs, like that, and the other one has a charge of 0. We know that electrons move from that to that, right? And if we look at that, we know that we have Q nu is equal to minus 3.6 nanocoulombs plus 0, and that upon 2 tells us that each sphere is going to have a charge of 1.8 times sorry, I'm getting ahead of myself here, and that gives us 1.8 nanocoulombs. So each sphere is going to have a charge of 1.8 nanocoulombs. And if each sphere has a charge of 1.8 nanocoulombs, how much of the charge is transferred here? It would be 1.8 nanocoulombs, right? Since the one sphere is neutral. Let's go to the next one. Here we have one object having a charge of 4.8 nanocoulombs, right? And we also have an identical neutral object, and then during contact, minus 2.4 nanocoulombs of the neutral object is transferred to the positive object, and then both objects are separated. What is the charge? So here again we can say, all right, the one is plus 4.8 nanocoulombs and the other one is 0, right? And in this case your electrons get transferred there. If we look at this here again, Q nu is equal to Q1 plus Q2 upon 2, right? Which is then equal to plus 4.8 nanocoulombs plus 0 all upon 2, and that gives us plus 2.4 nanocoulombs, which would then imply that the charge that is going towards the sphere is equal to minus 2.4 nanocoulombs. Let's go to the next one. Here you have an object with a charge of plus 3.2 nanocoulombs and the other one with a charge of plus 5 nanocoulombs. Right, they are then separated. So we know we've got the one with plus 3.2 nanocoulombs, and a nano, you know, is equal to 10 to the minus 9 right? So it means 10 to the minus 9 coulombs, and the other one is plus 5.6 nanocoulombs. Right, and as I've illustrated earlier, you know that electrons move from a less positive to a more positive. Okay, you know which direction it is. So we just need to ascertain how much is actually being transferred. So we say Q nu is equal to Q1 plus Q2 all upon 2, right? Which then gives us plus 3.2 Newton coulombs plus 5.6 Newton coulombs, right? Coulombs divided by 2, and that gives us plus 8.8 Newton coulombs all upon 2, and all upon 2, and that gives us 4.4 nanocoulombs, right? And if we're looking at how much was transferred, and if we look at that, we've got the result is 4.4, which means each one having a charge of plus 4.4, and therefore what has been transferred here is 1.2 nanocoulombs. Right, and if 1.2 nanocoulombs gets transferred to this, the resultant charge would be 4.4, and the other one as well. Right, now let's look at charge quantization. Charge quantization essentially indicates that charges are quantized, right? And what does it mean? What does charge quantization means is that let me first show it to you here. An object charge will always have an integer multiple of the electron charge, right? So that we're saying that the charge on an electron is quantized. It's discrete. You don't get half an electron or a quarter electron. An electron has a charge of 1.6 times 10 to the minus 19 coulombs. So from what we're doing here, charge quantization cannot be inferred from our experiments, right? Other experiments have been done. For instance, Millikan discovered that the charge on an oil drop is an integral multiple of the charge on an electron. He did these experiments with oil drops that were suspended within an electric field, and he discovered that the charge on the oil drop was always an integer multiple of the basic electronic charge. And this he found within the limits of experimental error. And then there was a bold assumption saying that charges are quantized. At that time, all scientists didn't agree, but as time elapsed, we now accept that charge is quantized. Right, and here we have this relationship where we say Q is equal Q, right? Q, which is the charge on the object, and N is the number of electrons, and Q is the charge on an electron, and we know what is the charge on an electron, right? So how many electrons are transferred if an object has a charge of 7.5 times 10 to the minus 6? Okay, so here the charge is positive in a sense, right? So which means it has probably it has lost electrons. So if we look at this, we know Q is equal to N times QE, right? Q, which is Q is equal to, let's see here, I've got, so if we want to know how many electrons, so it's N is equal to Q over QE, okay, which is then equal to the charge is 7,5 times 10 to the minus 9 coulombs all over the charge of an electron, which we take as 1.6 times 10 to the minus 19 coulombs, right, per electron, which then gives us our coulombs would cancel out, and that gives us 4.7 times 10, 4.7, right, 4.7 times 10 to the 10 electrons have been transferred. Okay, now let's look at conductors and insulators. Here I said I will talk about conductors and insulators, and I gave you a brief description of what an electroscope is. So let us suppose, for instance, we have an aluminium coated pith ball, and that's on a silk thread, and then we join the ball to the knob of the electroscope, right? So if we now place a negatively charged rod on a ball and we observe the leaves, we find that the leaves diverge, right? And if we substitute it with silk, we find for the copper nothing happens. Right, now let's look at this here. I have this particular pith ball that's negatively charged. Here we got an electroscope, and I told you that's the metal rod. So here's our gold leaves there. That's our metal rod. And what happens, this is a neutral electroscope. So if I got a charged pith ball and I connect a copper wire here, I find that the charges move towards the leaves, and when they move towards the leaves, these leaves actually repel. Right, so that means that copper wire is actually conducting those electrons, and it's allowing it to move through to the leaves of the electroscope. So we consider it to be an conductor. If I now replace that and I use a silk thread instead, and a silk thread is considered to be an insulator. And if it touches the knob, we find that these leaves remain. They do not diverge, which indicates that silk is an insulator. It doesn't allow the electrons to move through that particular material. Right, so we have here right. So the leaves of the electroscope do not diverge because the charge has not been conducted, right, by the silk. Now, conductors, what are they? Essentially, they conduct electricity. Metals are good conductors, and they offer little resistance to the flow of charge. Insulators, we know most of our non-metals are insulators. They do not readily transfer electrons, and the materials that can't, they don't have a flow of charge, and the non-metals are usually non-conductors. Right, we know that. Now let's look at the next exercise. Here we have an object which has a charge of minus 0.5 coulombs. Oh, that's the last charge, and another one with 1.5 coulombs. I expect these charges usually to be in the nanoscales and the micro coulombs and nano coulombs. But nevertheless, let's use that particular charge. So if we want to know what's Q nu, here Q nu is equal to minus 0,5, right, coulombs plus 1,5 coulombs all upon 2, that would be equal to 1.0 coulombs all upon 2, and that would give us 0,5 coulombs, right? Okay, and that would be plus 0,5 coulombs. So you need to specify that, which gives us an indication that if it's 0,5 coulombs, that the sphere has lost electrons, each of those. Right, now let's look at the next one, and here we see that the charge is 8 times 10 to the minus 17 coulombs. We want to know, does the body have a shortage or excess of electrons? Does it have a shortage or excess of electrons, and how many electrons are involved? Right, since the charge is negative, it has an excess of electrons, right? So since charge is negative, it has an excess of electrons. And now if you want to determine the number of electrons, so we say N is equal to Q upon QE, which is equal to 8, that's negative, 0.0 times 10 to the minus 17 coulombs all upon minus 1.6 times 10 to the minus 19 coulombs per electron, we said, and which then gives us 500 electrons. Okay, 500 electrons. Right, now, how are electrostatic charges generated? We know that they are generated when objects, right, objects are rubbed together. Rubbed together, right? So when objects are rubbed together, we have electrostatic charges. Alright, let's look at the next one. We've got two charged objects with a charge of minus 6 nanocoulombs and the other with a charge of plus 9 nanocoulombs. And they are brought into contact and then separated. Now, is there a shortage or excess of electrons on the body carrying the minus 6 nanocoulombs? Alright, the fact that it's minus, we know that there is an excess of electrons, right? So, as an excess of electrons, okay? Now, how many electrons are involved in your answer above? Okay, so we know we have Q, which is a charge on that sphere, and that is given to us by N, and Q, the charge on the electron. So N, or the number of electrons, is equal to Q over QE, right? Which is then equal to minus 6 times 10 to the minus 9 coulombs, since we know that the nano coulomb is 10 to the minus 9. A nano, then you have that a prefix 10 to the minus 9. And that over 1.6 times 10 to the minus 19 coulombs, and I'll shortcut that and say coulombs per electron, or say coulombs per electron, right? And which then is equal to, which is then equal to which is then equal to 3.75 times 10 to the 10, right? 3.75 times 10 to the 10 electrons. Okay, now, what charge does each sphere of the objects carry after the separation? Okay, so we know we have Q nu, which is equal to Q1 plus charge on Q2, all upon 2, which is then equal to minus 6 nano coulombs plus 9 nanocoulombs, and that gives us 1.5 nanocoulombs, and that's a plus 1.5 nanocoulombs. So each sphere has 1.5 nanocoulombs of charge. Right, now let's look at the next one. A charged body has a shortage of 2000 electrons. What is the charge on the body? Right, it has a shortage of 2000 electrons. So let's say, for instance, we know 1 electron has, let's do this, say 1 electron, okay, has a charge of minus 1.6 times 10 to the minus 19 coulombs. Right? Coulombs. So we say, therefore, 2000 electrons will have a charge of 2000 times 1.6 times 10 to the minus 19 coulombs, right? Which gives us 3.2 times 10 to the minus 19 coulombs, okay? But it has a shortage of this charge, 3.2 times 10 to the 3.2 times 10 to the minus 16 coulombs, and since it has a shortage, the charge on it is going to be plus 3.2 times 10 to the minus 16 coulombs. Right. Let's go on to the next one. Now here we have a triboelectric series, and we would like to know what happens when a glass rod is rubbed vigorously with silk. So in order to answer this, we need to go to the triboelectric series and have a look where the relative positions of these two materials are. And there we are. If we see, we've got glass. Glass is here. Glass is here. There's glass. And here's silk. Right? As you can see, glass is above silk, and glass loses electrons. So it's going to be positive, and silk is going to be negative when the two materials are rubbed together. Right, so here we have it. We've got our glass, okay, and that loses electrons electrons, and then it becomes positively charged. You got our silk, which gains electrons and it becomes negatively charged. Becomes negatively charged. There you have it. And see you next time.